So the tree diagram problems bring up a couple other issues for us that we want to consider. For one thing, it helps if you're making a tree diagram that you know how large it's going to be by the end. That way you can double check yourself when you've made it that you've made the right size tree diagram. But for another thing, if it's a very large sample space, something with lots of different branches, you wouldn't want to make a tree diagram because it'd be too complicated. Tree diagrams are really just for about small problems. Don't get me wrong, there are plenty of small problems that the tree diagrams are helpful for, but we wouldn't want to make tree diagrams for really complicated problems. All right, so that means we want a way to be able to determine our sample size ahead of time. I want to be able to figure out how big my sample space is and what I need. And that's where the multiplication rule of counting comes in. Not to be confused with the multiplication rule for probabilities, that's going to show up in 5.3, and we'll worry about that then. But this is just how can I figure out how big my sample space is going to be? So if a task consists of, task consists of a sequence of choices in which there are P selections for the first choice, Q selections for the second choice, R selections for the third choice, and so on. The task of making these selections can be done in P times Q times R, ... different ways. And notice those dots are actually at the level of the multiplication dots. And what that means is you would keep multiplying and multiplying until you get to the last task. So this rule is really helpful for us in finding our sample spaces. Also the size of our tree diagrams because they're one and the same. All right, now let's go on to a couple examples. So here I have us looking at the biological sex of biological sex of a family with 6 children. So, and again, we're assuming only male, female possible. This should be very familiar to you because we've already done it. But essentially you say, okay, for the first child, that's the first task. So the first task has how many options? Well, male and female are the only options, so that's 2. Second child, well, the second child, again, male, female is possible, so 2. Third child, 2. Fourth child, 2. Fifth child, 2. Sixth child, 2. So that would mean that there are 2 to the 6th options. Here, let me make this larger for you all to be able to see here, which is equal to 64. That's how many different options there are for a family with 6 kids. I know I said it on the previous page, but I figured it was worth just reiterating one more time. So 2 times 2 times 2, that's the first 3 kids, and then 2 is the second 3 kids, and you multiply it all together, you have 6 kids. Now, we're going to toss a fair coin 4 times. Well, when you toss a coin, you're really interested in heads and tails. And just like with the biological sex of children, we assume that there's only heads and tails possible, which is actually not true. You technically can flip a coin and have it land on the edge and stay there. It's pretty rare. It's about a 1 in 10,000 shot, but nevertheless, it is possible. So we have hold on, let me make this just 1 second here for you guys to be able to see this. There we go. So we have 2 options for the first coin, 2 options for the second coin, 2 options for the third coin, 2 options for the fourth coin, and we stop there because we're only going to do this 4 times. That means that we have 2 to the 4th, which is 16 different options. It wouldn't be fun to do it, but you could. All right, now what about a fair 6-sided die and a fair 20-sided die? Well, when you toss a 6-sided die, which is the normal die you think of when you think of a die generally, there are 6 outcomes possible, right? So there are 6 sides, 6 outcomes, no trouble. Then you're going to toss a 20-sided die. Well, 20-sided dice have 20 sides, funnily enough. And I'm just going to show you these on the exam notes packet, which quite frankly, in Chapter 5, you should take out of the back of your course pack and staple together and start using it all the time because you're going to need it for all chapters from here on out. Put your name on it, staple it, and use it. So a 6-sided die is set numbers 1 through 6. A 20-sided die is numbered 1 through 20. So there's 6 sides and 20 sides. And so you would multiply 6 times 20, which is 120, and that would be how many different possibilities there are. And you definitely would not want to do a tree diagram of that either. That's way too large. All right, now Yahtzee is a game I used to play a lot of when I was a child. I doubt I was actually playing it correctly, but I was playing it. Now Yahtzee is you throw 5 six-sided dice, and you're interested in getting sixes if I remember correctly. But you're throwing six-sided dice, so there's 6 options for the first die, 6 options for the second die, third die, fourth die, fifth die. So there's 6 to the 5th options, which would be, and I'll just grab a calculator, 6 to the 5th, which is 7,776. Here's the calculator in case you don't believe me. 6 to the, that's the caret button, raises it to the power of 5. Enter. See, 7,776. And oh boy, is that not anything we want any part of drawing a tree diagram for. Nope, nope, nope. That would be terrible. All right, so now what about talking about cards? So I'm going to begin with a standard deck, obviously, because that's where most things begin. Sorry, I'm having some problems with my computer there. There we go. So we're going to do with replacement first, and then we'll do without replacement. So when we work with replacement, we want to think about the fact that we're putting the card back in. So that means that we have 52 cards for the first choice. But because we put it back in and randomly select, we have 52 cards for the next choice, and then 52 cards for the third choice. So if you were, I don't know, playing a magic trick and everybody always put their cards back, hypothetically speaking, it'd be 52 to the third. Okay? So 52 to the third, which is, let me grab a calculator, 52 to the third, 140,608. So that's what this would be, 140,608. Little comma right there to make it easier for you to read. And there you have it. So that's how many different 3-card drawings you can make. Sorry, my computer was giving me grief there. All right, now we're going to try it without replacement. So without replacement. So when we draw the card, we don't put it back, which is actually more how card games tend to work, right? When you're dealt a card, it's not like you put it back in, you play your hand. Okay, so if the dealer deals you 1 card, then there's 52 options for that first card. But you have it in your hand now, so that lowers how many outcomes there are left for the deck. So that's 51 options, and then times 50. So with each draw, you're lowering how many possibilities there are. And it would keep going like that. So 52 options for the first card you're dealt. Now there's only 51 cards left in the deck, so when they deal you again, there's only 51 options, and they deal you again, there's 50 options. So I'm going to grab a calculator. 52 times 51 times 50, which is 132,600. It's interesting to note that when you do this without replacement, there's actually less outcomes possible than with replacement. So without replacement lowers how many outcomes are possible because you're restricting yourself. With each card you deal, there's less there. This is also called, by the way, a permutation, if you've ever heard of that word. Also, permutation. We are not necessarily going to cover that, but that's what it is. It's a permutation. If you've ever seen the symbol, it looks like this. There's 52 cards, you're choosing 3. So that's what it would look like in notation. Sorry, what was this? 132,600. So that's what this is. And you can find that with a calculator. But again, don't worry about it. I'm just mentioning that in case you're ever in a math class and a permutation comes up. All that means is you're selecting and selecting items, but not replacing them back into the deck. In this case, we're selecting 3 items from a total possible 52. In some sections of the course, we sometimes cover section 5.5, and that's where permutations would show up. But if you're not in a special section like the honor section that would cover that, then you don't have to worry about it. All right, we're all done with that problem with the multiplication rule of counting. So I'll see you back here for another video where we compare the classical and empirical probabilities amongst other things. See you then.